All right, hey everyone. So this is chapter 7, solids, liquids, and gases. All right. So just a heads up, I've reduced the workload for Alex, but I didn't change the PowerPoints. So everything is still going to be on the PowerPoint, but I'm going to go through and show you what you don't need to learn. And so I've kind of looked at what we're going to be doing in Chem 2, or what, excuse me, you will be doing in Chem 2, and there is nothing that I've taken out that you're at risk of seeing again. I don't think, okay? So Chem 2 is a lot less math, a lot more organic and physical and biochemistry. So you're going to see less math, more concept oriented things. So I've pulled out certain parts that I don't think are necessarily relevant to the nursing field or to what you're going to be doing in the future. All right. So with that being said, you might want to check Alex and see what topics are still on Chapter 7. I pulled out at least two topics, but I think I've also pulled out individual sections within each topic. So um, a lot less workload for Alex, I think, on this chapter, even though they seem to be getting more and more intense as it goes along. I've reduced chapter 7 by a little bit, and I hope this helps everybody kind of get this done faster and minimize all of the extra stuff that we're having to learn. Okay? So, the three states of matter, we're looking at chapter 7 today. We've talked about the three states of matter, right? Solids, liquid, gas. And we saw that they have different properties. Solids are fixed, they stay in one place, they don't move around any hardly. Um, Liquids fill the container they're in, uh, but they're still very tight together. They kind of rotate around each other and move like water. I think about like water, how water moves across each other, but it always stays kind of together. It's still in the glass, but it's all moving within that little space. All right, now gas is much more spread out. There's much more space in between the particles. It's bouncing around everywhere. Bounces off the walls, bounces off each other, and they just are in constant motion. Okay, and we talked about this motion in another way, right? Kinetic energy is temperature. How fast the individual particles are moving or whatever, that is the indication of temperature and the kinetic energy of that molecule. Um, let's see, the kinetic molecular theory of gases. So this is just saying that those particles are always moving. Okay, they move randomly, they move rapidly, they bounce into each other, they bounce off the wall. How fast they're moving is an indication of temperature, but they don't really connect or bounce in or like combine with each other typically. They bounce off each other and they bounce off the wall. And so this this force where, let me pull up my paint pad real quick. This force where particles are moving around in a space, in an enclosed space, and bouncing off the walls, it creates this force that we call pressure. Okay? So what I'm going to do here is draw like a little balloon. Um, and I'm going to put some gas particles inside of the balloon here. Okay? And then if I think about it, I really have gas particles outside the balloon too, right? This is just air out here. All right? So what happens with pressure? Pressure is any force exerted on an area, a certain amount of area. We talk about it in like pounds per square inch if you're talking about a tire. So that means that if you say you have 35 pounds per square inch, I have 35 pounds of weight pressing on each square inch of area. All right. So let me pull back up this PowerPoint so you can see the equation. Pressure equals force divided by area. The force exerted per unit area. All right, and there's a bunch of different terms here, so you'll need to be able to go back and forth on these. Atmosphere is probably what we use the most because it's usually about 1. That's just the atmospheric pressure around you. So on our balloon, that would be everything pushing in this way is roughly about 1 atmosphere. Okay, it gets much lower as you get higher in the sky because there's more room for that gas to expand, right? If I'm down close to the surface, I have a bunch of stuff on top, atmosphere, stratosphere, and it kind of all compresses down and then creates this nice little tight space where most everything is about 1 atmosphere. But there are other units that we use. The torr, the psi, which is the English unit, so we use pounds and inches as opposed to millimeters for this is mercury. Hg stands for mercury. So if you remember a thermometer measures temperature. We know what temperature is now, right? It's kinetic energy. So if I keep the temperature constant and allow the pressure to get to that mercury, it can also be adjusted by the pressure that's pushing on that mercury. So we use millimeter mercury as a unit for pressure. Torr is basically the same thing as millimeter mercury. Just makes it so you don't have to say millimeter mercury. And then Pascal, which is this PA on the bottom, is just another unit that we can use to kind of say it's usually for higher values. We call them kilopascals. Just another unit for pressure. All right. So now let me go back to my balloon. Hold on, let me make sure we ain't. Yeah, we're going on Boyle's law, so I'm going back to my balloon. All right, so these particles on the outside, the air presses on the balloon. That's about 1 atmosphere of pressure. But the balloon has gas particles in it that press outward. Okay? And that's because these particles are trapped in a space and they bounce off each other and they bounce off the walls, and it creates this constant pressure on the outside walls of the balloon. And that's what keeps it expanded and looking like it's filled or whatever, nice and tight, stretched out, because that pressure is the same at every point on the inside of the balloon. That's the kinetic molecular theory, okay? Everything bounces, all the gases bounce into each other, they go back, they bounce off the walls, and we end up with a equal pressure distributed all around the inside of that container, okay? So, now we have these gas laws. Gas laws kind of tell us what to expect when we adjust the temperature or the pressure or the volume or the moles of any of these enclosed systems. Okay, so I like to think about the balloon because it's enclosed, but you can also think about the atmosphere, right? The atmosphere has gas pressure all around you at all times. There's constantly oxygen and nitrogen and carbon dioxide and all of these gases that are floating around beside you at all times, and they're constantly bouncing off each other, bouncing off you, and you feel a 1 atmosphere pressure around you mostly all the time. Okay? So now the gas laws are just a way that we can, it's a math equation, and it gives us some predictability about what it means, what gases behave like, and what they do. Now, they call it the ideal gas law because it's not like perfect, okay? It's very close, but not quite perfect. And because there's always something else that kind of happens, right? Like, say, 2 molecules combine, right? We weren't accounting for that in our ideal gas law, so that might change a little bit the numbers that we're getting back out of it. All right, let me clear this off, and I'm going to write a new equation, and this is called the ideal gas law, okay? PV equals nRT, all right? So now let's go over a couple of terms that we're going to use from here on out that kind of it's easier ways to talk about relationships. Okay, the relationships between, say, pressure and volume, or temperature and pressure. So let me write in what all of this is. P equals pressure. Okay, actually, I don't think I have to write all this. I think it's on the slides here. I'm going to skip down to ideal gas law. And you'll see why I'm skipping this, because I want y'all to know, if you know the ideal gas law, there is a shortcut that you can use to get back to any of those other laws that we're talking about. We're going to talk about each one of them individually, but it's easier for me. Let's start with the ideal gas law. PV equals nRT. Okay? So pressure, P is for pressure, V is for volume. N, make sure y'all can still see me. Yeah, N is for moles, the number of moles that we have. R is a constant, okay? And R has several units behind it. Um, and you have to determine which pressure they give you so you can use the right R value, because each R value has a different unit for pressure. And so you have to make sure you match that up with the one that they give you. Usually we use the ATM one, because atmosphere is usually about 1 ATM, but not always. I mean, we have systems that we've created higher pressures, so not always. I'm just saying, usually we use an ATM. Um, and it's 0.0821, and then that's liter ATM up top, mole and Kelvin on the bottom. So we use Kelvin for the temperature. This last T here is for temperature. Okay, so we got pressure, volume, N equals moles. R is a constant with its own units, right? Really crazy units, liter ATM per mole Kelvin. But that cancels out everything else that's there. That's how come that has all of those units, because we need it to cancel out everything else. All right. And then T is for temperature. We express it in Kelvin, so it's important that you can go back and forth from Celsius to Kelvin, Fahrenheit to Kelvin, Fahrenheit to Celsius. All right. So now we have a math equation, and as I said, I put a video in. I'm gonna go to your content right quick. Gas laws shortcut. This is a good little Tyler DeWitt video where he shows you how you can maneuver the gas laws to make so you can come up with your own gas law, your own Charles law, your own Boyle's law. All these other laws are all based off of the ideal gas law. So if you know that, you can solve anything else dealing with gases. Okay? So that's where I would start, with the ideal gas law. Now let's talk about each one individually. All right, Boyle's law. Excuse me. Make sure y'all can see me. Boyle's law is something we use in diving. So I've done some scuba diving before, and Boyle's law. All of these gas laws are actually very important when you're talking about uh, going underwater or anything like that, because if you think about it, your lungs are essentially that balloon that I drew just a minute ago over here, right? Your lungs are like the balloon. And so when I start diving down underwater, I take on more pressure. It's not an atmosphere anymore. I've got water pressure. It acts the same way. The molecules are bouncing off of me, and it creates higher and higher pressures as I get lower and lower underwater. And so for divers, it's especially important that we know all of these laws so we can predict how our lungs are going to react, um, even when we come back up to atmosphere, because we're letting go so much of that pressure that your lungs will try to expand. The gases inside of them will try to expand too fast, and you end up getting what's called the bends. Nitrogen will try to escape the lungs and get into the blood system. So it's very dangerous stuff, and it's very important that we know these kind of laws so we can predict what's going to happen. All right. First up, let's talk about Boyle's law. Boyle's law says that pressure and volume are inversely related, inversely proportional. So I want to talk about that real quick. You're going to see some different kind of equations, and they might not make sense to you. So I'm going to kind of stop and explain them. All right, if you see something like this, that means pressure is directly related, meaning they go up at the same, related to volume. Okay? Proportional, even, I should say. Sorry about the writing here. Pressure proportional. What does proportional mean? Proportional means if one goes up, the other goes up at about the same rate. Okay? Proportional to volume. If you see this, let me erase all that. No, no, no. Cut. Alright. If you see this, P, and then the relationship sign, alright, that means it's inversely proportional. That means when pressure goes up, let me just put pressure up, volume down. Okay? So inversely proportional means that they do the opposite. If one goes up, the other goes down. Directly proportional, which was what this was, means that they both go up together or they both go down together. All right, so these are relationship terms we use a lot more in math, but we're going to use for these going forward. All right, let me cut that out again. And now let me tell you what it actually is. It actually is inversely proportional. And I think your slides actually probably do a better job of this. So let me go back there. So Boyle's law says that pressure and volume are inversely proportional. Inversely related, I should say. If one increases, the other decreases. And so they've got this little diagram here where you can see that, all right? Both of these cylinders have roughly the same amount of gas, okay? So when I increase the pressure on that press right there, that metal press, it's going to decrease the volume, okay? If I increase the volume, there's the same amount of gas pressing on the outside, but there's more outside wall, more area, so that's going to decrease pressure, all right? That's just one relationship. Uh, and you have an example problem here, so feel free to work through that. And you can use these equations here to kind of help you solve these problems. P1 V1 equals P2 V2. And now this P1 and V1 is just saying that the pressure in vessel 1 is 10 ATMs. The volume of vessel 1 is 4 liters. I changed the volume to 6, so that would be my V2 actually right here. That should be a 2. Yeah. And then P2 would equal what? So I'd rearrange this. I'd say 10 times 4 equals 40. 40 divided by 6 equals, doesn't say. 40 divided by 6 equals roughly what? 6.66, something like that. So 6.66 ATM pressure in the second one. All right, so that's fairly simple. Um, but you do have to, you can write these down on a little card and then have them there. But like I said, I think the ideal gas law, if you learn that, you can automatically, you hear my dog back there sleeping or something, uh, automatically determine whether or not it goes up or down. Okay? But you can obviously use these equations. P1 V1 equals P2 V2. That's Boyle's law. Now we're going to look at Charles's law. Charles' law has to do with temperature. The volume of the gas is proportional to its temperature. So remember what that means. If something's proportional, it goes up together. Inversely proportional means when one goes up, one goes down. So you're going to see these words: proportional, inversely proportional. Uh, you need to be aware of what they mean. So first off, make sure you use Kelvin. If one quantity increases, the other increases as well. Okay? So the same little diagram, except for this time it's V1 over T1. Wait, V1 over T1 equals V2 over T2. All right? So you can rearrange that to solve any of the Charles Laws problems. This is about for a fixed amount of gas at constant volume, the pressure is proportional to temperature. So remember the last one, Charles' law, was about volume. Uh, Gay-Lussac's law is about pressure and temperature. As temperature goes up, pressure goes up. As pressure goes up, temperature goes up. All right? And why is that? Because we talked about the kinetic theory, right? Molecules are moving. If I increase the temperature, they move faster. If they move faster, they hit the outside walls harder, right? So that's how you can kind of think about pressure and temperature being proportional. If I increase the temperature, these molecules move faster. They hit the outside walls. They hit each other with more speed. That creates more pressure. Okay. So if as long as you keep all of these things straight in your head, you shouldn't ever go the wrong way, right? If you know what's proportional to each other or what's inversely proportional to each other, and you see the pressure go down, then you need to assume my temperature goes down as well. All right. If you get an answer that doesn't show your temperature going down, that means you've made a mistake somewhere, and you've made them inversely proportional. All right. Next up is they combine the gas laws so that pressure, volume, and temperature are all in there. Um, and that's fine. It doesn't account for the number of moles. So if all things being equal, they have the same number of moles, you don't have to worry about that. Now, Avogadro's law is what deals with the moles. Okay, the volume of gas is proportional to the number of moles. So as the number of moles goes up, the volume goes up. If volume goes down, the number of moles goes down. All right, all things else being equal. All right, and then some more practice with Avogadro. We're not going to stop there too long. The ideal gas law, that is the bread and butter. Okay, so let me pull back up my pad and show you something there. All right, so we've just talked about all these three different laws and what they mean, right? One's inversely proportional to the other, blah, blah, blah. I'm going to show you something real quick. Let's say that I want to solve for just pressure. All right, how would I do that? I need to divide both sides. Oh, no, don't do that. I need to divide both sides by volume. Okay, volume cancels. Pressure equals nRT over V. Okay, so now that I have my pressure isolated, I can look at this ideal gas law and tell what my relationship is with any other thing. Okay, so in a sense, the ideal gas law is derived from all of those other laws. And as such, I can go backwards and derive any of those laws from this gas law. So here's what we're going to do. Let's say I've never seen Charles' law, um, Boyle's law, Gay-Lussac's law, or uh, the Avogadro's law. Okay? But I know this equation, the ideal gas equation. Let's say they gave me a pressure and they want to know how the volume changing will mess with it. So let's just check it out. Let's say my pressure is 1. All right. I'm going to pull it over here. 1 ATM. All right. How will that be affected if I change any one of these other things on this side? Okay. So let's say my initial volume was 2 liters. Okay, I'm going to take this off. All right. 1 is equal to nRT divided by 2. Okay, so as this number goes up, excuse me, let me get my pen. As this number goes up, this number has to go down. All right. And if I remove everything else, the nRT from here, you'll see that P equals 1 over V. That looks a lot like the inverse proportion that we made earlier for Boyle's law. Okay, let me back up again. Now let's do temperature. All right, so P still, let's say still 1 ATM, nRT over V. And I'm going to replace this, cancel that. I'm going to replace this T with actual temperature. So let's say 40 Kelvin. 40 Kelvin equals 1 ATM. Now let's say I make it 80 Kelvin. Okay? 80 Kelvin. If I double that, it's just going to double the left side. So that makes 2 ATM. So pressure is directly proportional to temperature, right? That's Charles' law, or excuse me, Gay-Lussac's law right there. So all of these laws are derived from this equation. If you know this equation, you should be able to work through any of the other problems. What you do is you just set all these equal to 1. Set that equal to 1, set that equal to 1, set that equal to 1. All right, and then P equals T. If P goes up, T has to go up. The only one that's inverse is volume. So that could be, you could just remember that. But if you rearrange your equation like I've done here, you'll see that V ends up on the bottom, which is why it's inversely proportional. All right, let me see where we're at on the PowerPoints. And that's just a lot of math that you're going to have to go through and do over and over, get your practice in. Dalton's law and partial pressure. So I've pulled that. I'm pretty sure I pulled that from I can't remember if I did or not, if I pulled it from Alex. But either way, all of the pressures, partial pressures added together equals the total pressure of the system. So this is just straight addition. You'll take the pressure of each gas, and they'll give you a pressure for each gas, and then you add them all together to get the total pressure of the container or the atmosphere or whatever it is that they're asking you about. So that's Dalton's law, and it's pretty straightforward. Okay? The total pressure of a gas mixture is the sum of the partial pressures of its component gases. So this is air, essentially. It has nitrogen, oxygen, carbon dioxide, and water. All of these pressures add together to give about the standard atmospheric pressure. All right. So we are going to talk about these intermolecular forces just a little bit. I don't think I left some in there, mostly due with hydrogen bonding, I think, because we have seen this before, right? When we were talking about melting points and stuff earlier on in the semester, we said that different things can create molecules having lower boiling points or higher boiling points. A lot of that has to do with these intermolecular forces. Okay, so like water creates a lot of hydrogen bonding, which means its boiling point is relatively high considering other carbohydrates like methane and stuff are always gas at room temperature. Water is a liquid, and that's because it has extra hydrogen bonding between oxygen and hydrogens. All right. So let me start with hydrogen bonding because we know the most about that. Water, right? Hydrogen is slightly positively charged. Oxygen, um, fluorine, nitrogen are all slightly negatively charged. So it creates these kind of bonds. We call them hydrogen bonds. And it's usually between oxygen and hydrogen or a nitrogen and a hydrogen. The slightly positive hydrogen will find the more negative elements and start to create these little weak bonds with them. So that's why water stays liquid up until 100 degrees because these hydrogen bonds are holding them kind of together. That's why water flows kind of together and kind of stays tight to each other because of the hydrogen bonding. Now, London dispersion occurs with carbohydrates or hydrocarbons. So when you have a bunch of carbons kind of linked together, um, those charges can get distributed to one side or the other of the molecule. And then so them charges will build up and they'll align themselves with the opposite charges of another molecule. And so what you ends up having is you have this little chain of hydrocarbons that are kind of slightly bound to each other. All right, they hold on to each other just a little bit, not as much as water and hydrogen bonding, but just they do kind of hold each other tighter together. These are called London dispersion forces. And now the other one is a dipole-dipole interaction. Um, that's kind of a mixture of hydrogen bonding and London dispersion. So this is an oxygen is slightly negatively charged. The carbon here is slightly positive. So they will start to line up in this manner, kind of like we saw with this one, except for these forces are a little stronger. Okay, so they hold a little tighter, and the charge will not move off of that oxygen. Okay, for example, let me make sure y'all can still see my cursor. So this red is the oxygen. It's always going to have that negative there. All right, this carbon is always going to have this partial positive charge here. So essentially, they are always going to line up this way. When it comes to London dispersion forces, something can make this change. If I introduce a hard positive charge right here somewhere, it might force this away and bring the negative over here, right? So London dispersion forces can kind of change as the environment changes. Um, but dipole dipole and hydrogen bonding are always that because oxygen is always slightly negative, hydrogen is always slightly positive, carbon is almost always slightly positive. So it will always create these same kind of forces or dynamics in bonding. Okay. So those have a lot to do with melting points and boiling points. Uh, Ones with lower forces will become gas more easily. Uh, Stuff with higher forces, so like the hydrogen bonding I said was the strongest of those. Those are typically going to be liquid or solid more often than the ones with less, like London dispersion forces or something. Now, as stuff gets really big, it has to be a liquid or solid just because of the weight. So that doesn't really indicate anything. All right, now everything else is dealing with liquid and solid. I'm trying to see what all I left on Alex, but we're getting pretty close to the end here. It's good to know these different terms for, gas changes or phase changes, I should say, states of matter becoming something else. Evaporation is when liquid is converted into gas. Condensation is when gas is converted into liquid. And then we also have from liquid to solid. Where's that at? Liquid to solid is freezing. So when I think about phase changes, I usually think about ice and water. Um, when I freeze something, it goes from being a liquid to a solid. When I melt something, it goes from being a solid to a liquid. Okay? So it doesn't have it there. But just so we're understanding the phase changes, there's different words. So if you see condensation, evaporation, that should tell you that there's been a phase change. It's went from a solid to a liquid, or a liquid to a solid, or a gas to a liquid. Something has happened. Vapor pressure. So anytime you have a glass of water or a glass of coffee or tea, anything, there is a certain amount of molecules that are being ejected from the top of that glass, and sometimes you can smell it. Right? If I smell over alcohol or anything, I can smell that alcohol coming out of the glass. That's because these molecules are actually bouncing into each other and it's ejecting one out of the top. And so that's what you see. This is kind of a diagram of that. Vapor pressure is what lifts those scents or whatever molecules out of the glass as a gas. So you smell it, it's in gas form, but it is quickly converted back into liquid or whatever, and then you can smell it. So vapor pressure is pressure exerted by gas molecules with the liquid in equilibrium with the liquid phase. So most everything's liquid, but it shoots out a gas particle every now and then, just because the energy of what all the bouncing around and everything, eventually one will collide into each other, and they'll give this molecule enough energy to become a gas. All right, and then viscosity, surface tension. Um, this is just kind of how fast something moves. So I've got a coffee cup here. Let me see. Let me pull this up. I've been wanting to take a sip of this for a minute anyway. So here's my coffee. It is about the same viscosity as water. Viscosity is how well something flows. Okay, like a river flows down the river. Whatever, water flows down a river. Um, if this were molasses, I could tilt this cup and everything wouldn't fall out immediately, right? It'd slowly fall. Syrup is another one that's very viscous. Viscosity is just how well something flows, okay? How fast that liquid will flow. So viscosity is only concerned with liquids. Molasses is the slowest of all the liquids, right? I can turn it upside down. It might not even fall out. It might just barely start to move. That is a very viscous substance. Water is not very viscous. It just splashes out everywhere. This coffee is probably a little more viscous than water, but not much, because it has a couple little heavier compounds in there, like caffeine and stuff, sugars. Um, so that's viscosity. Um, and technically it's a measure of the fluid's resistance to flow freely. But I just think about it as how well does it flow. Uh, Viscous materials do not flow well. Molasses is a very viscous material. Honey is a very viscous liquid. Uh, what else? Yeah. So anyway, water is not very viscous and it just kind of flows freely. Once I dump it out, it flows out and it'll keep flowing until something finally stops it. And intermolecular forces have a large indication of what is viscous and what's not. As I said, as you have more sugars and stuff like honey and molasses do, it gets a lot thicker, and those start to create these kind of London dispersion forces, and they kind of get stuck real tight to each other, so they don't want to move away from each other like water does. You know, they want to stay real tight together because they got all these different forces. Molasses might have all the forces working in it, depending on like because of how slow it is. I'd say it probably has London dispersion forces in there. It's probably got hydrogen bonding going on, and it's probably created some type of dipole-dipole interactions. So it has all of those things working to help keep it more solid-like than liquid. But it is a liquid, and it does flow. It just takes a long time because of all the intermolecular forces. All right, surface tension. It's the measure of resistance of a liquid to spread out. So water actually has a high surface tension. You see these bugs can kind of sit on top of water. Um, that's because the hydrogen bonding is stronger than the weight of that insect. Okay, those forces would hold together more tightly than that insect being able to pierce down through those forces. All right, and then do we need to know anything about solids? Um, yeah, I'd go through here and just kind of look over the terms, but I'm pretty sure I pulled most of this from your Alex. I know I pulled all of the energy stuff. So I pulled specific heat, and I also pulled the heating and cooling curves, which I think would have had to. Yeah, I pulled all energy and phase changes from Alex, so you don't have to worry about that for the test. You don't have to worry about none of that math. Don't have to worry about the heating and cooling curves. So I think that's it for this chapter, actually. All right. So now you're welcome to go through and kind of learn a little bit more about this. Here's the table that I was looking for with all the different terms. This table might actually be good to have. So I don't think I asked you about it in Alex, but I would keep this around for the final just because we saw this in several different sections, and I don't know, I might use it. Okay. The only other ones we didn't talk about, we talked about melting, freezing, vaporization, condensation. We didn't talk about sublimation or deposition, and that is just going straight from gas to solid. Typically, you have an in between, right? If we think about water, it goes from ice, water, gas. Okay? Solid, liquid, gas. Uh, Sublimation and deposition skip that liquid phase. So it goes straight from solid straight to gas. I think about dry ice. Dry ice is a sublimation process. It goes straight from a solid piece of ice into a gas. There's no liquid puddles in between. So that would be sublimation. Deposition would be the making of dry ice, um, where it goes from a gas to a solid. All right. I think that is about it. I'm at 45 minutes. Yeah, so that's good. We're kind of reducing our workload, but make sure you go in there for those other videos if any of this was confusing. Okay? I know we kind of move fast. We're moving faster than the in-person classes for sure. So you're doing a great job. Email me if you have any problems, and let me know how you're doing on your Alex. If there's something I didn't cover, if there's something that you need more help with, you can email me and I can post another video or do some practice problems myself. So I haven't been hearing much from everybody. Y'all let me know where you stand and how you're doing. Um, Good luck, and I'll see you next week.